Welcome to Chemipedia, chemistry classes for 11th and 12th standard. So in this video, I am going to discuss a simple trick to find the number of lone pairs of electron in inorganic molecules. Okay, right? So here we have to follow some steps. Step 1, we are supposed to know the group number of the element. First thing, we should know group number. The element belongs to which group. Then second thing, the valency of the element, valence electron, or which is nothing but valency of the element. Okay, so if you know these two things, group number as well as valency of the element, we are able to find out the total number of lone pair of electron present in inorganic molecules. Okay, right. Now for example, I have written the second period elements starting with lithium followed by beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Okay, right. Now lithium belongs to group 1a, likewise beryllium 2a, boron 3b, then carbon 4b, nitrogen 5b, oxygen 6b. Oxygen belongs to group number 6b. Then fluorine 7b, neon inert gas belongs to 0 group, isn't it? Right. And the elements which are following these elements also will belong to the same group number, isn't it? Right. Now for some group, the group number is nothing but valency. For example, lithium, beryllium, boron, carbon groups, the group number is nothing but the valency of the elements present in that group. For example, lithium group number 1, so that valency also 1. Likewise, beryllium group number 2, valency 2, boron valency 3, carbon valency 4. So that in this first 4 group, the group number is nothing but their valencies, isn't it? Right? Then the next 4 groups, nitrogen, oxygen, fluorine and neon. For them, the valency is nothing but 8 minus group number. Valency is nothing but 8 minus group number. For example, nitrogen group, nitrogen, phosphorus, arsenic, antimony, bismuth, isn't it? Nitrogen group belongs to 5th B, isn't it? So that the valency is nothing but 8 minus group number 5. 8 minus 5, 3. Nitrogen group valency 3. Likewise, oxygen group 2. Halogen group, fluorine, chlorine, bromine, iodine, the valency is 1. So inert gases, they have octet configurations, isn't it? So they have less tendency to combine with other elements, so that their valency is considered as 0. Now from this group number as well as valency of the element, we are able to predict the number of lone pairs of electrons. Okay, so right, let us discuss some examples. The first one is XeF2, xenon difluoride. Okay, right. Now xenon only belongs to inert gases, isn't it? So that xenon has 8 valence electrons. 8 valence electrons. So that these are nothing but the valence electrons of xenon. Totally there are 8 valence electrons. Nothing but xenon configuration. Xenon outer electronic configuration. Then fluorine atom valence is 1, which means fluorine is capable of making one bond, isn't it? Right. There are 2 fluorine atoms. So that there are 2 bonds possible between xenon and fluorine, isn't it? So this is the way how the 2 fluorine atoms are making bond with xenon, isn't it? Right. So in this molecule formation, xenon is using 2 electrons, these 2 electrons to make bond with fluorine atom, so that there are remaining 6 electrons which are not used in bonding. So these 6 electrons are nothing but lone pair. The pair of electron not used in bonding is nothing but lone pair. So 3 pair of electrons in this molecule not used in bonding. So this molecule has 3 lone pairs of electron. Okay, right. The next example, xenon tetrafluoride, XeF4. So this is a xenon configuration, 8 electrons, valence electrons, 4 fluorine atoms, isn't it? So fluorine makes bond with xenon, isn't it? So that xenon uses only 4 electrons. These 4 electrons for making bond with fluorine. So that remaining 4 electrons are there, which is not used in bonding, isn't it? So that xenon tetrafluoride, there are 2 lone pairs. These are the 2 lone pairs. Okay, right. Then third one is xenon hexafluoride. Xenon hexafluoride. So this is xenon configuration. Here also fluorine, isn't it? So fluorine valency 1, which makes one bond with xenon, isn't it? Each fluorine is capable of making one bond. 6 fluorine atoms are there, so that xenon will use 6 electrons to make a bond with 6 fluorine atoms, so that one more pair is left unused, isn't it? So that xenon hexafluoride, it has only one lone pair. Okay, right. Then the next example is ammonia. So here nitrogen has 5 valence electron, hydrogen valence is 1, so which means hydrogen is capable of forming one bond, isn't it? So this is nothing but the valence electronic configuration of nitrogen with 5 electrons. Each cross is 1 electron, isn't it? Then 3 hydrogen atoms are making bond with nitrogen, which means nitrogen uses 3 electrons to make bond with hydrogen. Among the 5 electrons, 2 more are left, isn't it? Left unused. So that forms one lone pair. In ammonia molecule, there is only one lone pair of electron. Okay, I think you know the structure of ammonia, pyramidal shape, isn't it? So in which 3 electrons of nitrogen used to make bond with hydrogen atoms, 3 hydrogen atoms, the 2 more electron which is left just above nitrogen atom, which forms the lone pair. Okay, right? The next one, PF3 molecule, which is similar to ammonia molecule, isn't it? Phosphorus belongs to nitrogen group now. So like nitrogen, phosphorus also has 5 valence electrons. Fluorine valency 1, so which means it forms one bond, isn't it? So this is the outer electronic configuration of phosphorus, 5 valence electrons. 3 fluorines are making bond with phosphorus. So phosphorus uses only 3 electrons, the remaining 2, one lone pair. Okay, right. PF3 and NH3 are similar molecules, each with one lone pair of electron. Now let us go to some little bit complicated molecules like XeO2F2. XeO2F2. Okay, right. Here the central atom xenon, inert gas, so 8 valence electrons. Oxygen valency 2, which means it is capable of making 2 bonds. Fluorine valency 1. It can make one bond, isn't it? Right. Now, so this is nothing but xenon configuration, 8 valence electrons. Now in the compound there are 2 oxygen atoms, isn't it? So each oxygen is capable of making 2 bonds. Now this oxygen makes 2 bonds with xenon, isn't it? Another oxygen also making 2 bonds. So that to make bond with 2 oxygen atom itself, xenon is using totally 4 electrons. Okay, right. Then there are 2 more fluorine atoms. Fluorine is capable of forming only single bonds, isn't it? 2 fluorine, so forms 2 bonds. For making bond with fluorine atom, xenon using 2 more electrons. So altogether, the xenon uses 6 valence electrons. 4 to make bond with 2 oxygen atom, 2 electrons to make bond with 2 fluorine atoms, isn't it? So that 2 more electrons are left unused, which forms one lone pair. Okay, right. The next example number 7, ICl4 minus. So here you are given an anionic space, isn't it? Polyatomic ion, isn't it? Right. Now here the central atom is nothing but iodine. So this is the valence electronic configuration of iodine. So iodine belongs to halogen group, so that halogens are having 7 valence electrons, isn't it? But net charge you are given minus, isn't it? So that 7 plus 1, there are 8 electrons totally. There are 8 electrons around the central atom. Okay, right. Now with the central atom, we have 4 chlorine atoms, isn't it? Chlorine belongs to halogen group, valency 1, which means it can make one bond with the iodine, isn't it? So that the 4 chlorine atoms are making single bond with iodine, isn't it? So apart from this, which means iodine is using 4 electrons for making bond with 4 chlorine atoms, so that remaining 4 electrons, so it forms 2 lone pairs. Okay, so this is a charged species, so negatively charged species, so that along with the valence electron of the central atom, we have to add the number of electron equal to its charge. Suppose if we have a charge 2 minus, you have to add 2 electrons with the valence electrons. Here 1 minus, so I have added 1 electron. Okay, right. The next molecule is water, isn't it? Next molecule is water. Central atom oxygen, 6 valence electron. Hydrogen bonded with oxygen, valency 1 for hydrogen, isn't it? Right. Now this is the valence configuration of oxygen atom, 6 electrons, 2, 4, then 6, isn't it? Right. There are two hydrogens bonded with oxygen through single bond. In the sense, oxygen is using only 2 electrons to make bond with hydrogen. So therefore, remaining 4 electrons, which forms 2 lone pairs. So this is nothing but the structural formula of oxygen. I think you know that, which is called as bend shape. What is it? Bend shape. Now you can see just above the oxygen atom there are 2 lone pairs, isn't it? Right. Then the next one, hydrogen sulfide. Hydrogen sulfide. Here central atom sulfur, so which belongs to oxygen group. But like oxygen, this also has 6 valence electrons. Hydrogen valency 1. But this is the valence configuration of sulfur atom, 6 electrons, 2, 4, 6, isn't it? Right. There are 2 hydrogen with sulfur, isn't it? So for 2 hydrogen is making single bond. Each hydrogen making single bond. In the sense, sulfur is using only 2 electrons for bonding, isn't it? Remaining 4 electrons, which forms 2 lone pair. Okay, right. Then another species, a positive species, H3O plus. H3O plus. Central atom on the oxygen. Central atom is oxygen. You know very well, oxygen has valence electrons about 6. Valence electrons 6. But here the net charge is plus 1, isn't it? About 6 minus 1, only 5 electrons will be there. 5 electrons, okay. Right now, this is the electrons which are exhibited by oxygen. 5 electrons. Actually, oxygen has 6 electrons. Due to positive charge, this 1 electron will be removed off, okay. Only 5 electrons are left over. Right, and then with oxygen, how many hydrogens are combined? 3 hydrogen. So that the 3 hydrogens are making single bond with oxygen, isn't it? So in the sense that oxygen is using only 3 electrons. So that remaining 2 electrons are there, which forms as single lone pair, which forms 1 lone pair. Okay. So positive charge, positive ion, okay? You have to subtract number of electron equal to its charge. Then the next one, another similar example, ammonium ion. What is it? Ammonium ion. Right here, central atom nitrogen, 5 valence electrons. But net charge plus, so subtract number of electron equal to charge. 5 minus 1, 4 electrons. So oxygen configuration, actually it is nitrogen. What is it? It is nitrogen. So in nitrogen configuration, we have 4 electrons. Actually valence electron 5. Because of carrying positive charge, this electron will be left, isn't it? Right. Then 4 hydrogens are combined with nitrogen, isn't it? So these 4 hydrogens are making single bond with nitrogen, which means here in this species, nitrogen is using all its 4 electrons which is available, isn't it? So that no more electron left unused. So it has no lone pair. Okay, ammonium ion does not carry any lone pair of electron at all. Okay, right. Then the last example, IF2 minus central atom iodine halogen group. So totally 7 valence electrons are there, but net charge unit negative charge. So you have to add electron equal to its charge. 7 plus 1, 8 electrons. So this is the electronic configuration of iodine. 7 electron plus 1 extra electron. Okay, due to the negative charge. Right, now with iodine we have 2 fluorine atoms, so that 2 fluorine makes 2 single bond with iodine, which means the iodine is using only 2 electrons. So that 6 electrons are left unused. So that in IF2 minus, the total number of lone pairs is about 3. Okay, right. So this is a simple trick which is used to find out the number of lone pairs of electron present in inorganic molecules, even positive and negative charged species also. I hope you understood. Right, thank you and keep watching my videos.